Okay, in this video, I'm going to be discussing the key features of cubic functions. Now, a cubic function, just so we all know what we're talking about here, is a third degree function. Okay, so that means that this is a polynomial where the highest power on x is x to the third power, or x cubed, hence cubic function. So we're going to get into some examples here. We're going to talk about specific key features depending on which examples we're talking about. So the first problem here, example 1, it says given the function f of x is equal to just simply x cubed. And we are asked to sketch the graph of the function. Now, I know what a cubic function is. I know what it looks like. But if you're not sure what it looks like, I'm going to go ahead and split screen. And I'm going to open up Desmos. And I'm going to use Desmos to graph this function. It always takes a little while for Desmos to pop up. So this function right here, instead of f of x, I can be lazy and just write y equals. All right, so down here I'm going to put y equals x. And now to get it to the third power, if I look over here, I have it, a squared, which is great, but that's not what I want. But if I use this a to the b, it pops the little cursor up, so it's now a superscript, which is what we want our powers to be. And so I'm going to put a 3 here. Now, this is a little crowded for me, so I'm going to go ahead and close this part over, so I'm just looking at the graph. And ladies and gentlemen, this right here, this red curve, is a cubic function. So first thing I'm asked to do in the notes is to sketch the graph. Okay. So I'm just going to sketch a quick graph here. Goes through the origin, okay? And it does continue both directions, top to bottom, okay? So I'm going to go ahead and close out Desmos for right now. I'll get back to it because I'm sure there's going to be more examples. All right, so based off of this sketch, I want to identify the domain, the range, the x-intercepts, and the y-intercepts. That's it. So remember that your domain are your possible x values. So how far to the left does this graph go? How far to the right does this graph go? And if we look, this graph is slowly, right, as it's dropping, it's getting further and further to the left. And then as it's increasing here, it's getting further and further to the right. So what's its domain? Well, it's going to be eventually everything. Negative infinity to positive infinity. Every x value in the whole wide world works. All of them are fine. Now we're going to talk about range. Range are your possible y values. So how low does this graph go to how high does this graph go? Well, if we look at our graph here, this thing's going to keep going forever and ever low. And as we increase here, it's going to keep going forever and ever to the infinities. So range here is going to be negative infinity to infinity. All right, x-intercepts. So this is where we cross. Wow, I don't know what I was trying to write there. Hold on a second. There we go. Let's go. Okay, I can spell, I swear. Cross, there we go, the x-axis. Now in this case, we're only going to cross the x-axis in one position, and it's the origin, all right? And the origin here is 0, 0, okay? It only crosses the x-axis one time. Y-intercept, it is where you, let's see if I can do this right, cross, there we go, the y-axis. And in this case, we again have one y-intercept. It's the same exact place as the x-intercept. It's the origin, 0, 0. Okay, so that's the basic cubic function. Okay, that would be the parent function. Now we can change it. We can stretch it. We can turn it. We can twist it. We can do all kinds of things to it. And that's actually what we're going to get into in the next couple of examples. So if we look at example number 2, okay, now initially you might look at this and say, wait a minute, that's not a cubic function because there's nothing in there that says x cubed. You're right, except when we take a linear expression times another linear expression times another linear expression, so first degree times first degree times first degree, we actually end up with a third degree polynomial or third degree trinomial. It's not trinomial, try it again, a cubic function. So I'm going to take this and I am absolutely going to throw this into Desmos and see what we end up with. So let me go ahead and split screen here. And this time I'm going to leave Desmos up because we're actually going to use it a lot more. So I'm going to go ahead and eliminate this equation I had before. So I'm just going to hit the little X button here. All right. So y is the same thing as f of x equals. So x plus 3 times x minus 1 times x plus 2. Okay. Now I am going to go ahead and push this over so I can have better access to the graph here. All right, so quick sketch, and this is just a sketch, so it doesn't have to be perfect. I'm not looking for exact values on the graph. I will get those exact values when we start looking at the key features. Okay, so quick sketch, I've got the sketch. It's about the right idea, good enough. Okay, domain, how far to the left, how far to the right? It hasn't changed. So we can still go all the way to the left, we can still go all the way to the right. Any x value is fine. So negative infinity to infinity. All right. Range, how low to how high? Well, this graph keeps going forever towards negative infinity. Does a weird little kind of curve here around the origin, but ultimately it goes to positive infinity as well. So range values, negative infinity to infinity. Okay. X-intercepts. Now I'm going to tell you two ways you can find them because I want you to be aware mathematically what's going on or algebraically what's going on, and then also graphically. So I'm actually going to talk about the algebraic version first. So if I look at my factors here, I have three little factors, right? Each of these linear terms. So what I can do if I'm looking for my x-intercepts is I can set each one of those values, right, each one of these little factors equal to 0, and I will be able to solve for my 3. You'll notice there's 3 places I cross the x-axis, my 3 x-intercepts. So let's see, minus 3, so that's going to get me negative 3. So one of my x-intercepts is going to be negative 3, 0. I don't need a comma there, so let me take that out. If I add 1, I would get positive 1. So I would have 1, 0. And then for my last one here, I'm going to subtract 2. So that would get me negative 2. Now, a couple of things you may notice. For each one of these, it's the opposite value to what's attached to x. So x plus 3 turns into the x-intercept of negative 3, 0. Then x minus 1 becomes positive 1, 0. X plus 2, that plus 2 becomes a negative 2. All right, so that's the algebraic kind of idea of what's going on here. Now, because we have the tool, we can use Desmos as well. So what I'm going to do is come over here on Desmos, and I'm going to tap the graph with my finger. It kind of highlights the graph, and you'll notice all of these little gray dots that kind of started to appear. So these gray dots have meaning. Let's tap on all 3 of the ones that are across the x-axis. So there's that one, 1, 2, and whoo, look at that. Those are our x-intercepts as well. All right, so that's kind of nice. So for our y-intercept, algebraically, we could absolutely replace x with 0. So 0 plus 3, 0 minus 1, and 0 plus 2, and then figure out what our y-intercept is based off of that. Totally works, right? Mathematically, you would have y is equal to 0 plus 3 times 0 minus 1 times 0 plus 2. You could throw that in a calculator. Or if you do the math really quickly, it should be 3 times negative 1 times 2, which would be negative 6. So 0, negative 6. Okay. But remember I said there's a whole bunch of these little gray dots? Well, there's a little gray dot down here that's right on the y-axis. Well, look at that. There's our y-intercept as well. Okay. Now, there are 2 other gray dots here, and they're the relative maximum and relative minimum points. Now, in a cubic function, there is no absolute maximum value because this graph keeps going towards infinity, all right? But there is a relative maximum here, where basically this is the maximum our graph gets to in this area. So I'm going to go ahead and just tap that dot and figure out what it is. And I'm literally just going to steal the point here. So this is relative maximum. And the relative maximum is negative 2.535 and then 0.879. Okay, that's our relative maximum. It's the maximum value other than going to infinity. This is what's called a relative minimum. It's the lowest value other than going towards infinity completely. All right, so let's go ahead and hit that little point there. Relative minimum, negative 0.131 and negative 6.065. All right. Now, your relative minimum and your relative maximum break up your graph into a couple of pieces. Now, what I just did there, because you'll notice all the little points disappeared, is I actually just tapped the graph to make all the points disappear. I'm going to tap it again because all I want are the max and min, the relative maximum and the relative minimum. Now what's going to happen here is these break up your graph into little sections. So your graph is doing something until it gets to this relative maximum. It does something else until it gets to the relative minimum, and then it does something else to infinity. Now, when we talk about these somethings, our graph is either increasing or decreasing. Okay, it's not both. You can only do one at a time. So as we look at this graph from negative infinity until we get to this first maximum here. So from negative infinity to negative 2.53, this graph is increasing. All right, so that's our first interval of increase. So from negative infinity to negative 2.535, that's the first x value on your maximum here, your relative maximum. Now, between this relative maximum and this relative minimum, this graph is dropping, right? This is decreasing. So that interval of decrease is going to be from negative 2.535, and I'm just taking these numbers directly from Desmos, to negative 0.131, we are decreasing. And then from this relative minimum to positive infinity here, and it's not that it's going to positive infinity on the y-axis, it's that as this moves across the x-axis, your graph is increasing, okay? That's where I'm talking about the positive infinity. So negative infinity over here on the x-axis till this first x value, interval of increase. From this x value to this x value down here, this is decreasing. And then from this x value to infinity, the function is increasing, all right? So I'm going to go back to my interval of increase here, and this is going to be from negative 0.131 to infinity. We are increasing, okay? So that's all of the information for example number 2. I'm going to go ahead and slide on down to example number 3, all right? Of course, if you have any questions or concerns, let me know. Now, example number 3 is pretty much like example number 2. We have a fraction here, but not a big deal, especially if we're using Desmos. We'll let the technology figure this all out for us. So I'm going to go ahead and get back to the equations here. So hit the little double arrow. I'm going to eliminate this equation that I currently have and start a new one, okay? So y is equal to negative 1 over 4. Now, how did I get the over 4 part? It's just division sign, okay? Now, to get myself out of the denominator, I'm going to go ahead and hit the right arrow key, and you'll notice the cursor pops over. So let's see, x plus 4 times x minus 3 times x minus 2. Okay, I want to do a quick check to make sure that I didn't screw up my function in some way. So I'm just going to arrow over, make sure I've got all the right pieces. Okay, so negative 1/4 x plus 4, x minus 3, x minus 2. Okay, got the right function. So I'm going to hit the double arrow to hide the function. So I'm just seeing the picture here. All right, so the first thing, sketch the graph. It doesn't have to be perfect. It's just give me the idea that you know what's going on with your graph. Okay. Now we're going to identify all the same features that we found in the last function. So first things first, domain. For a cubic function, your domain is going to be negative infinity to infinity. Any x value is positive, any y value is, or actually I'll say it, any y value is positive, which means possible, not positive. All right, let me try that again. Any x value is possible, which means your domain is negative infinity to infinity. Any y value is possible, so that means your range is negative infinity to infinity. All right, now for your x-intercepts, let's take a look at the function, right? See if we can figure it out that way. So each of these little linear functions, remember you can just take the opposite of what's attached to x because all of these have a very simple x value. There's no coefficients there. It doesn't say 2x or 3x. So x plus 4 is the x-intercept of negative 4, 0. X minus 3 is the x-intercept of 3, 0. And x minus 2 would be 2, 0. All right. Now to verify, I'm going to go ahead and use Desmos. I'm going to tap the graph and then tap the 3 points on the x-axis. So negative 4, positive 3, and 2. Yep, I've got all my zeros. Clear that out. For my y-intercept, I could make x equal to 0, multiply this all out, and then multiply it times a negative 1/4. So let's see, 4 times negative 3 is negative 12, times negative 2 is 24. 1/4 of 24 is 6, should be a negative 6, I think. So I believe my y-intercept is 0, negative 6. To verify, I'm going to tap the graph on Desmos, tap the y-intercept, and I am correct. Okay, so we've got the domain, the range, the x-intercepts, and the y-intercepts. You know how to find those now algebraically, I hope, and both Desmos, right? Nice tool. Let's talk about the relative maximum point, all right? Now, we've got this point right here is a relative maximum. All right, coming up to it, you got this, the graph is increasing and then going away from it, it's decreasing. That's a relative maximum. So I'm going to tap the graph, right, get all those gray points on there and then hit that top point right there. So relative maximum is going to be the point 2.519, 0.407. Okay. Identify a relative minimum point. So a relative minimum point is going to be when your graph is decreasing, it hits a relative minimum and then it increases from there. So this is a relative minimum point. And that is the point negative 1.852, negative 10.036. Okay. So let's talk intervals of increase and intervals of decrease. So our graph here starts in the upper left portion and is dropping until it hits this first interval or first minimum point. I'm going to say the right term here. So it's dropping till it hits this relative minimum. So this means we are decreasing, right? Graph is dropping from negative infinity until negative 1.852. Okay. So these intervals, when we're talking about interval of increase and decrease, are based on the x values. So right here is that negative 1.85, all right? So from here to here on the x-axis, we want to look and see what's happening to our graph. And this part of the graph is increasing. So between those two x values, the minimum value of negative 1.852 to our maximum value of 2.519, our graph is increasing. And then from this maximum point until positive infinity, this graph is dropping. So that's going to be a decreasing interval. Let me get in here. So that was positive 2.519 till infinity. Your graph is decreasing. Okay. All right, there is one more example here. I'm not going to make a video for it, but I will put it in the key so you guys can see what the actual answers are for it. So this was a lot of information about key features for a cubic function Use Desmos as a good tool here to graph some of these functions and find some of those key features, but you are going to need to understand how to get the intervals and how to get the relative maximum, relative minimum, like which ones are which. All right, so if you have any questions or concerns, drop me an email message and let me know how I can help.